Ladies and gentlemen, this brings us to our last example, example F. Example F is a little bit interesting and a little bit more complicated than the previous ones. Example F deals with the idea of half-lives in radioactive decay. Okay, a half-life measures how long it takes a radioactive sample to decay to a non-radioactive material. But it's how long it takes half of it to decay. So if you have 10 grams of radioactive material, after one half-life, there would be 5 grams. After and then another half-life, half of that would decay. We're not going to get into what that all is. It's just a half-life, and the idea of radioactive decay is a very good example of exponential functions. So here we're dealing with the sample radon 222, which is, if you remember your chemistry, just its mass number, protons plus neutrons. So radon has a half-life of 3.8 days. This one decays very quickly. Some half-lives can be in thousands of years, like carbon-14, which is used for carbon dating. Thousands of years of half-life, but this particular one, very short half-life of 3.8 days. So we know that there was a 500 kilogram sample, okay, and we want to know the percentage of that sample remaining after 20 days. Okay, so you're going to think right off the bat, we're thinking 500 is our initial condition. After all, there was 500 kilograms of the radon. However, it does ask percentage. So that 500 kilograms represents 100%, or 1 when written as a decimal. This actually simplifies the problem, makes the math a little bit easier for us. Okay, now our B value. Remember half-life? So half of the sample decays. So that's telling us very clearly that our B value is 1/2. And since 1/2 is less than 1, this is decay. Which is interesting, which fits into the fact that it does use the word decay in the problem. Okay, so we're going to go ahead and, since it's talking about percentage, we'll use P for percentage of the sample remaining. So percent of sample remaining. So it's going to return a percent. And T will be our time again. And this time it's in days, because our half-life is in days, and our requested, so we're going to say it's in days. Okay, so that means we're looking for P of T. Our function, the percentage after time. So our initial value is going to be 1, very simplify it, to the 1/2. Now here's where this problem gets a little different. It's not just going to be T, because it's not got a half-life of 1 day. It takes 3.8 days for it to do one of these 1/2. So so it's going to be our T, the amount of time, divided by 3.8. We want to know how many half-lives, just tell you what this is, make sure you can see it. This is T divided by 3.8. This is telling us how many of those 3.8 half-lives fit into our time. So we are looking for P of 20, which is going to be 1 times 1/2 times 20 for our T divided by 3.8. Now be careful typing this in calculator. Remember, we need the 20.38 to be completely in the exponent. So make sure you put that in parentheses when you attach it as an exponent. And so when we do that, we end up with 0.026 approximately. Remember that was 1 because 1 stood for 100%. So if we rewrite this as a percent, we get 2.6%. So according to our problem, after 20 days, there will be 2.6% of the sample remaining. The interesting thing about a half-life is it never actually reaches 0. We continue just to keep taking a half of a smaller and smaller amount, so it does approach 0 but doesn't actually reach it, which fits into our idea of a exponential function. Thank you very much.